Okay, we have coils. Gave you the diameter of the coil. In the case of the coil you have, it's either average diameter, and it doesn't vary much. It only varies about 10% from inner diameter. So the average diameter of a coil is going to be about 2.6 or 3.5 centimeters. Okay? Wire lengths, I gave you the wire lengths. Okay? And those lengths were 20 feet or 200 feet. Okay? Number of loops, easily calculated from the length and the diameter of the coil. You know, each loop is a circle. So I don't have to tell you where that came from. Okay, EMF, something you should know, like all the way back to March, okay? And at least back to a couple of classes ago when we mentioned it. But now, really know it, is the rate of change of magnetic flux. And it's opposite to the change in the magnetic field, or the flux. Flux is what? It's field times area. You have so many coils, each has so many areas, right? Each has some area, and you got some magnetic field. So it's really easy to calculate the magnetic field if you have all these parameters. Okay? I mean the flux, if you know these things. Okay. Then the derivative is very simple, right? Total area is just n times the area of a single loop, so it just depends on the rate of change of the magnetic field. And if you got an iron core, for the iron we happen to have in the lab, I would have expected a little higher, but we're getting anywhere from 5 to 15 times the magnetic field that you would have without the iron. And that's just because the domains in the iron line up with the magnetic field in such a way as to give you a stronger magnetic field. It's like you got little magnets in this thing that are randomly oriented. All of a sudden they're all oriented parallel to the magnetic field, so they all contribute to the magnetic field. And you get a greater magnetic field. Okay, well, now your magnetic field is some multiple of current. Well, you just measured the current and the magnetic field in the coil, right? Okay, so you can figure out what that multiple is. And now you know if you run a current through, if you measure the current, you know what the magnetic field should be. And if you change the current in some way, di dt, it's just going to be related. Well, dB dt is just going to be directly related to di dt by whatever this multiple is. Okay? So all that makes sense. So you're going to be able to figure out the inductance. We're not going to take time within the lab to figure out the inductance. You'll do that later. I'll figure out a ballpark. Just to give us an idea how much inductance we have, because what we're really after is this big old chunk, this 100-pound chunk of iron wrapped with wires, and we want to see if we can observe the effect of its inductance. Okay? That's where we're headed. That's tricky. I don't think we've ever managed a really good observation. And what we really want to do is try to observe that by observing if we get a resonance in an LC circuit. Driving an LC circuit, okay? It's an LRC circuit because the wire has resistance in it. Okay, so that's kind of where we're headed. It's going to be tricky. Don't know if we'll manage it or not. Don't know if I could manage it without your help. Don't know whether that would be better or worse. And simply because it's a question of whether I would do this better working by myself without anybody else distracting me, or whether I would screw it up less if other people were throwing out ideas at me, right? And I don't know whether you will be better at it than I would, okay? Especially since there are three of you to distract each other, you might be much better. Okay, so let's see what happens.